Hey everybody, welcome to today's lecture for analysis of algorithms. This lecture is lecture number 6 and covers graph coloring. This is the first graph algorithm we're doing in the course, and it's the first of many, so let's hope this is a good start. So the first question you have is probably, what is graph coloring? And I'm going to describe it by going back to the origins of the problem. So where it comes from is something called the map coloring problem in the Middle Ages. And what it's about is, let's say you were tasked to draw a map. If you drew sort of the outline and then drew the borders of the countries, it's very hard to see where one country ends and the next one starts, right? So if we look here, it's hard to see the boundary between, say, South Africa and Zimbabwe. One technique that cartographers use to make these boundaries more clear is they give adjacent countries a different color. Right? So if you were coloring this map, you'd make sure that South Africa and Zimbabwe had different colors. Now it's much easier to see where the individual countries are. So we want to make sure that countries that are next to each other don't have the same color. Now, can you think of a simple solution to that? Well, the simplest solution is figure out how many countries there are. Let's say 210. I'm making that up. It may be nothing like 210. And just use 210 colors. Just give every country a different color and move on. Okay, now this solution is suboptimal, and certainly in the Middle Ages it was, because there were not that many pigments available. So there's not many different colors you can use. So you want to reduce the number of colors that you're using on this map. And there's an interesting reason that you can do that. It's quite possible for two countries to have the same color with no problems, right? As long as they're not next to each other. So if we look at South Africa and Tanzania, they have the same color, but you wouldn't think Tanzania is part of South Africa because they're not next to each other, right? There's quite a big gap between them. So we only want to make sure that adjacent countries don't have the same color, and we want to use the minimum number of colors. Okay, so why? Why do we want to do that? Well, visibility is one reason, right? Like we talked about, we want to make sure we can see that the countries are different countries. And the second constraint is ease of production. We want solutions with a smaller number of colors so that it can actually be implemented. Okay, but you're not a map maker, right? I mean, you may be. I'm not a map maker. And so this problem becomes super uninteresting, right? I don't care about map coloring. It's just, I mean, it's interesting, but I just don't care. So if we look at this problem, assign colors to countries on a map such that no adjacent countries have the same color. It's kind of uninteresting. How we can make it more interesting is by turning it into an abstract solution, meaning one that can solve lots of different problems, including potentially problems I care about, right? So we can change the problem domain. At the moment, if I'm not interested in maps, then this whole thing is silly. But I can change the domain by changing it to say, assign colors to vertices such that no adjacent vertices have the same color. And it's the same problem as before, because all I've done is just change a couple of those words, but I haven't changed the substance of what the algorithm does, right? And so I've kept the word colors for no real reason. I could have said assign numbers or, some property to vertices such that no adjacent vertices have the same value for that property. But it's easier to just keep the word colors. Okay. Now it's less distracting. It's less about maps and it's more about just some abstract problem. But it also introduces the idea that I can just change the words out, and as long as I'm not changing the substance of what's going on here, then it's fine. It's still the same problem. As an example, graph coloring is mostly used for things like exam timetables, so for things like scheduling. And if I look at this statement, I can just change the words again to say, assign timetable slots to courses such that no adjacent courses have the same timetable slots. Okay, that's pretty reasonable. And then I can say what defines an adjacent course. Courses are adjacent if they share a student. What that'll do is that'll mean that by solving the same problem, I will find an exam timetable that doesn't mean that any student has to write 2 exams at the same time, which is great, right? Okay, so we said it's assign colors to vertices such that no adjacent vertices have the same color using the minimum number of colors. Okay, so the question is, how do we do this? And that's really interesting because actually nobody knows how to do it. Well, no one knows how to do it efficiently. Okay. This is in a set of problems known as NP-complete, which are sort of the hardest problems in mathematics and computer science and everything. These are the set of problems that you just do not want to end up with. And what's interesting about this set of problems and why there's that prefix NP is that there is no polynomial time solution for these problems. So, you know, we were expressing our time as like n squared plus 3n plus 5. So there's no polynomial, not n to the million or whatever, that'll solve these problems. Okay. If there are any solutions, they have complexities like 2 to the power n or n factorial, which are just such unpleasant functions that, you know, these problems are just awful. Okay, so if nobody knows, then I guess we're done. That's graph coloring over. You can all, no, you have to stick around. There's still a lot more to come. The lecture is not as short as it sounds. The point is, when we don't know how to solve something that efficiently, we say, okay, let's solve it approximately. Let's say, well, we can't do it perfectly, so let's do it sort of suboptimally. And so we restate the problem to say, let's assign colors to vertices such that no adjacent vertices have the same color and prefer solutions that use fewer colors. So now we're not saying find the minimum number of colors. We're just saying find some small number of colors. Okay, now this problem is quite solvable because, you know, it's quite vague to a degree. But what I want you to do now is pause the video and just think about how you might solve it. How would you solve the problem of assigning colors to vertices such that no adjacent vertices have the same color? Okay, I don't know how well you did at that, but hopefully the first solution you come up with tends to not do too badly. So let's think about what we'd do. Well, the simplest solution is I can just say, well, for any vertex, just color it using a color not used by a neighbor, right? That's almost the same as the definition of the problem. I just said, you know, let's say I'm coloring vertex 0. What colors do its neighbors use? Okay, don't use that. Use some other color. So I'm stating that algorithm as, while there is some uncolored vertex, pick any vertex and set its color to the first color that no neighbor is using. I should say pick any uncolored vertex. And then just set its color such that it doesn't violate our constraints, right? So let's look at how this plays out. Let's say I've got some palette of colors: green, blue, yellow, orange, white. I said, while there is some uncolored vertex, pick any vertex and set its color to the first color no neighbor is using. So I'm going to start with 0. I'm just going to go in order because, look, the algorithm doesn't specify, and I'm just going to go 0 to 6, right? So I pick vertex 0 and I say, what color can it be? Well, none of its neighbors are using any colors. So the first color in this list that I can use is green. So I'm going to use it. Okay. Then I move on to vertex 1. Now the first color that I want to use is green, but there's a neighbor using it, so I can't do that. So instead I use blue. Okay. When I get to vertex 2, I look at my list to say green. Is there a neighbor using green? Actually, no. So vertex node is using green, but vertex node is not a neighbor of vertex 2. There's no edge between 0 and 2. So I can set vertex 2's color to 0. Right? I'm happy with that. The next thing is I'm going to do vertex 3. Vertex 3 can't use green, so we use blue. It's not next to vertex 1, so it can use blue. I then get to vertex 4. Can I use green? No, because it's next to vertex 0. Can I use blue? No, because it's next to vertex 1 and vertex 3. So I end up coloring it yellow. When I get to vertex 5, is there a neighbor using the color green? No, so I can color it green. When I get to vertex 6, is there a neighbor using the color green? Yes. Is there a neighbor using the color blue? Yes. So I'll have to color vertex 6 yellow. And I got the whole thing done using 3 colors, right? There were 7 vertices, so at worst I could have ended up with 7 colors, but I didn't. I ended up with 3 colors, so that's not bad, hey? I think actually the algorithm did rather well with that graph. Let's look at another example. Now, in this example, we've got just another graph and we're going to color it, right? Let's follow the same algorithm. We'll start with vertex 0 and we want to color it using the smallest unused color, or the first unused color. We're going to choose green. Okay. Then we get to vertex 1 and we can still choose green, so we're good. We get to vertex 2. Now there's a neighbor using green, so we have to use blue. We get to vertex 3 and there's a neighbor using green and a neighbor using blue, so we use yellow. Vertex 4 can use green and vertex 5 can use green. So we got this done using 3 colors. Okay, that doesn't look terrible, but just by looking at it, I can see that there's a better solution, right? I could do this. Now, if we look at this, there's only 2 colors used for the same graph, and I didn't even have to use the yellow. You know, that's pretty great. So, what's going on here? Well, if I look at the solution that we had here, the problem is it painted itself into a corner. By coloring vertex 0 and vertex 1 both green, it meant that vertex 2 and vertex 3 sort of ran out of options to color themselves. So they were forced to have different colors, right? And the thing about it is that vertex 2 and vertex 3 are the ones that are hard to color. So the algorithm or the problem says that vertices that are adjacent can't have the same color, right? So any vertex can't use the same color as its neighbors. And vertex 0, for instance, only has 1 neighbor. So it's pretty easy to color it. Vertex 2 has 3 neighbors. So it's much harder to color. Now, by coloring vertex 0 and vertex 1 first, we made vertex 2 and vertex 3 even harder to color. So they were already hard to color because they had lots of neighbors, and now they were harder to color because their neighbors were using up valuable colors. So how we can get around it is we say, actually, let's color them in a particular order. Instead of just going 0, 1, 2, 3, 4, 5, let's sort them by degree. Okay, degree is the number of vertices. And then we just color them in the order of their degree, right? So we can look at the degrees here. Vertex 2 and vertex 3 have degree 3, and 0, 1, 4, and 5 have degree 1. That's just how many neighbors they have. Now, in the algorithm, all we've changed now is we've said, instead of just picking any vertex, pick the uncolored vertex with the largest degree and set its color to the first color that no neighbor is using. So, not a huge change, but let's see how this plays out. So the first thing is we start off with a blank graph and then we say pick the uncolored vertex with the largest degree. So it's either vertex 2 or vertex 3. Okay, so we picked vertex 2 and now we pick the first color that no neighbor is using. None of its neighbors are using any colors, so we get to use green. Okay, then the next iteration is going to say pick the uncolored vertex with the largest degree, and now that's vertex 3. Okay, so our options are green and blue, but green is taken, so we're going to color it blue. Okay. Okay, I had some issue with my sound there, so I've cut off and come back. Yeah, so where were we? Okay, so we said we get to vertex 3 and we can color it blue because green is used. Then after that, we can choose either 0, 1, 4, or 5, and we just don't care. So we'll pick maybe 0. We don't care because they all have the same degree, right? So let's say we pick vertex 0. It can't be green, so we can make it blue. Vertex 1, we can make it green. Vertex 4, we can make blue. And vertex 5, we can make green. So it played out not that differently to the previous one, but now we only use 2 colors. Okay, so we didn't make a huge change to the algorithm. We just said, instead of coloring them in some random order, color them in the order of their degree. And we got a much better outcome. And that's pretty much the final algorithm we're going to use. So it's just sort by degree, and then while there is some uncolored vertex, pick the uncolored vertex with the largest degree and set its color to the first color that no neighbor is using. But that's fairly abstract, right? I said that in English. So how do we make it more concrete so that it can actually be used on a computer? So the first thing is, instead of colors, we're going to use numbers. right? So we're just going to translate. We've got green, blue, yellow, white, and orange. That can be color 0, 1, 2, 3, and 4. Doesn't matter. Okay, then in terms of the algorithm, we don't know how to sort by degree yet. We've got some work to do there. And so then we can say while there is some uncolored vertex, okay, that's fairly straightforward. Pick the uncolored vertex with the largest degree. Well, if the vertices are sorted, which is this part, then I just pick the first one and I'm fine. And then set its color to the first color that no neighbor is using. Now that I don't really know how to do. So the first thing I'm going to talk about is how we sort by degree. The first thing is we have to find the degree of each vertex. So we've got some graph representation storing the graph in our computer, and we want to find the degree of every vertex. We talked about this in the previous lecture, and we'd use an adjacency list representation storing the sizes of the list because that gives us the degree of the vertex for free, right? So if I want to know how many neighbors I have, I just look at the size of the adjacencies list and I'm done. If I've got the degrees, I can just sort using some sorting algorithm like merge sort or quick sort. In Java, we can use the built-in sort function, and then the whole thing will cost us theta n log n. I'll do a video on why merge sort costs theta n log n, but we'll save that for the future. Okay, so the sorting part is done. The other part we didn't know how to do is how do we set the vertex's color to the first color that no neighbor is using. So the problem is now, let's say I've just got this adjacency list, right? I know, like I'm trying to color some vertex, let's say vertex 2, right? So vertex 0 and 1 are colored, vertex 2 is not yet colored. And I want to figure out the smallest color that's not used by a neighbor. So what I'd have to do is kind of look at all the neighbors and figure out, you know, what's the first color that isn't used. So an initial intuition might be that I could just keep a variable that stores the smallest color and I just set it to 0, right? So initially I'm saying the smallest color that we found that hasn't been used is color 0. And then I just iterate through all the neighbors, and as soon as I find that color, I increment the smallest color. So basically I say initially the smallest color I can use is green. And then if I find somebody using green, I go, okay, well, no, then I got to use blue. And I just keep going. Okay. So the cool thing is in the worst case, that's going to be theta n because I have to iterate through all the neighbors, and I don't know how many neighbors I have, but it could be n. The problem with it is that actually it won't work. The reason it won't work is, let's say I'm starting off with vertex 2, right? And initially I set S to 0 to say that, you know, green is the smallest unused color. And then I iterate through the neighbors. When I look at vertex 0, I'm going to say, oh, well, it uses blue. So that means I can still use green, right? So I keep going. I look at the next one and I say it uses green. Oh, okay, so I have to increment. I can't use green because this neighbor uses green, so I'm going to switch to blue. And then I'm done iterating. So even though 0 used blue, I can't tell anymore because I've already moved past blue. So then I end up coloring vertex 2 in blue, which is a real problem, right? Because I'm going to set vertex 2's color to blue, even though 0 is using it. You can see there's an error there. That should be a 2, not a 3. Okay, so that algorithm, although it was nice because it was theta n, it kind of sucked because it was wrong. It's obviously pretty important that it not be wrong. So what can I do instead? Okay, so I could change my algorithm so that, you know, instead of losing track of the fact that blue is there, I could just go back and do it again. So basically what I could do is I could say, okay, I want to color vertex 3. And at the start, the smallest unused color is green. When I look at 0, okay, it's fine, so it's still green. When I get here and it has to change to blue, then what I need to do is go back to the start and start iterating again. Okay? The problem with this is every time the smallest color changes, is I go back to the start of the adjacency list and I iterate again. So in the worst case, that could be something like n squared, right? Because I could have to iterate through the list n times for, you know, and each iteration costs n. So it's going to cost me n squared in total. So that kind of sucks. So what I do instead is I keep an array so that I don't lose track. So what I do is I make an array of colors. Now bear in mind this array might be confusing in that it looks like I've got 0, 1, and 2 as indices, and those are vertex numbers. They're not vertex numbers, they're colors. When I've got 0 here, it doesn't represent vertex node, it represents color node, which is green. Color 1, which is blue, and color 2, which is yellow, because what it's keeping track of is whether the color is used. Okay, so what I do then is I iterate through the adjacency list, and whenever a neighbor has a color, I set that color property to true. Okay, so when I'm iterating, I'm going to find vertex 0, which uses color blue or color 1. So I know color 1 must be used then, so I set this value to true. Okay, note it's vertex 0, and I'm not setting 0 to true because I'm not talking about vertex 0, I'm talking about color 1. Okay, color 1's value will change to true. When I get to vertex 1, similarly, I see how it uses green, so I've got to set color 0's value to true, meaning it's used, right? So this array is keeping track of whether the colors are used. Then when I'm done, I just iterate through this array looking for the false. Okay, so that's true, that's false. Okay, done. So then I can say the first false was yellow, so I have to set this vertex to be yellow. Okay, and this would cost me big O of n. Okay, notice I didn't say theta of n because theta implies that I know how much this is going to cost. I don't actually know how much this is going to cost in terms of n, where n is the number of vertices, because this vertex may have no edges. If it has no edges, if its adjacency list is empty, then the thing is just going to cost me nothing. The iteration is going to take no time because iterating through its adjacency list will be immediate if it has no adjacencies. On the other hand, it could be adjacent to every other vertex, in which case it costs me n-1 because there's n-1 vertices it can be connected to. So I don't know how much it's going to cost. I just know it won't be worse than n. So I'm going to put it in big O of n. Okay. So how much does the whole thing cost me? Well, sorting by degree cost me theta n log n. And then my while loop, I know it runs n times because it says while there is some uncolored vertex, color it. So how many times can you color an uncolored vertex? Well, as many times as there are vertices, which is n. Okay. And then it says pick the uncolored vertex with the largest degree. Now, if I'd already sorted it, then that's theta 1. I just take the first item and I'm done. Set its color to the first color that no neighbor is using. Okay, we already found that that takes big O of n. So the total cost is going to be big O of n log n plus n squared, which is going to give me big O of n squared. Okay, because the smaller term is going to disappear in the limit, right? So asymptotically, n log n doesn't matter when we have an n squared term. Okay, that's pretty much the end of our graph coloring thingy, but please read the stuff in the book because there's a lot that's covered in much better detail in the book than I've covered it here. So I hope I've given you a bit of an overview, but the book gives you a much better detailed view of this. Yeah, you're gonna have to code it in this week's lab. So it's a lot simpler than it sounds. It seemed like a bit of a long explanation for something that didn't need such a long explanation. I think you'll be fine with the lab. Okay, and there's a couple other interesting things about this problem. One is a thing called the four-color theorem. This theorem states that when we have a planar graph, which is a particular type of graph where edges don't overlap, they can sort of be drawn without having the lines cross each other. These planar graphs can all be colored using four colors. Interestingly, maps, two-dimensional maps like world maps, are all planar graphs, which means we can color a world map using four colors while still making sure that no adjacent countries have the same color. That's pretty cool, hey? Now, one of the cool things about this is this theorem was proven by a computer. It's the first theorem that was actually proven by a computer. And how it did it is by checking every possible graph. Now, all graphs can sort of be reduced to some set of special cases for this problem, and the computer just exhaustively went through all of them. Another interesting thing is the proof of R colorability. I'm not going to talk about that right now because I'm going to do an entire lecture on this. It's not going to be a super long lecture, but there'll be a lecture on it. and it's going to go up this week. So when you get to that part in the book, you can probably just skim over it because I'm gonna cover it in a lecture. Okay, so I hope that was not awful, and thank you for listening.